Greetings and welcome to session 2 of this course on organizational causes of large technology failure. This week we're discussing the work of Charles Perrow, a distinguished, really exciting sociologist, now retired from Yale University. He's written widely in organizational theory. The book we're focusing on, though, is Normal Accidents. So I wanted to bring out a few kind of preliminary ideas before we turn to the details of what the normal accident theory is. But first of all, what is the sociology of organizations? Why is there a field which is designated as the sociology of organizations? It is a specialized field of research on how organizations work. And you might say that organizations are the most pervasive element of the social environment in which we live. I suppose there are other competing structures that we also would want to give priority to. But organizations of all kinds are just an absolutely common part of our ordinary lives. And the sociology of organizations is a field of study in which the scholar investigates the arrangements, behaviors, norms and culture, power relationships, goals, and functioning of organizations, paying attention to the dysfunctions and failures which can arise in organizations as well. A point that Perrow does not make, but I believe it is really quite central, and so I'd like to introduce it today, is the idea of an actor-centered approach to the theory of organizations. The idea that an organization is primarily an ensemble of individuals with various powers, various interests, self-interests, and institutionally defined interests and organizationally defined interests. They have powers of command and leadership and discipline and training and so forth. But in the end, we simply cannot take the view that the actors within an organization are simply robots living out their job descriptions as defined by an org chart. Instead, we need to try to determine what are the interests, what are the priorities, what are the goals that the individual has. This approach, actor-centered theories of organizations, there are a number of people who take this approach, but a theory which I'm especially interested in is Neil Fligstein and Doug McAdams' theory of strategic action fields, which expresses this approach to organizational behavior. It is the idea that an organization involves multiple fields of power and influence, and the action, the behavior of the organization depends upon these contending coalitions. So why do we need to consider organizations when we're concerned about large technological failures? A chemical plant, a nuclear power plant, a dam, a ship, an airspace, all of these are locations where complex technologies are linked together into processes by engineering experts and designers, which are then executed by managers, operators, and executives. In other words, very large teams of individual human beings who have job assignments, who have reporting relationships, who have supervision, but their labor and their activity interacts so as to bring about either successful operation of the plant or the dam, or possibly unsuccessful operation, where, like at Bhopal, a major technology failure occurs. So we might look at the power plant or the chemical plant as a system designed by an engineer to function in a particular way. But I would put it to you that it's really valuable to look at the power plant as a complex social environment where individuals of various levels of skill, motivation, understanding carry out various tasks. And furthermore, we simply will overlook at our great risk this fact. It is the fact that organizations are directed, run, planned, investments are made by people whose interests are sometimes distinct from both the social interest and possibly also the interest of the organization itself. So decisions about investments and the organization of the process, which safety and equipment to invest in, what kind of safety processes to implement, these decisions are made by business executives who have a variety of motivations and priorities, and whose priorities may deviate substantially from the social priority of maintaining safe operations that protect the health and safety of the public and of the workers. The diagram here may be a little difficult to see. I think you can blow it up in the slides that are also provided. But it's my diagram to try to indicate that an organization has both internal structure, but it also exists within a larger environment. And the larger environment includes the state and the state's regulatory capabilities. It includes other kinds of stakeholders like other companies or shareholders. In other words, there are influences on the behavior of an organization which come from outside the organization. And then on the right side of the diagram, you see the results and output of the organization. And it might be the smooth production of Caterpillar tractor machinery, or it might be the production of a whole bunch of pollution and chemical toxic waste dumped into the Illinois River. In other words, positive or negative results, but we can look at the organization and as a kind of social space which is located in an environment of influences and also an environment which it directly influences. Here is, I think, a good quote. I've tried to take most of the quotes out of these slides because it was getting to be a fairly long presentation, but this is a good description from Perot of his account of what he's trying to do. I will dwell upon characteristics of high-risk technologies that suggest that no matter how effective conventional safety devices are, there is a form of accident that is inevitable. This is not good news for systems that have high catastrophic potential, such as nuclear power plants, nuclear weapon systems, recombinant DNA production, or even ships carrying highly toxic or explosive cargoes. It suggests, for example, that the probability of a nuclear plant meltdown with dispersion of radioactive materials to the atmosphere is not one chance in a million, but more like one chance in the next decade. That is a profoundly worrisome paragraph on page 1 of Normal Accidents. So far I've spoken about organizational features that are internal to a firm, internal to a corporation, let's say. But another organizational feature which is highly relevant to safety is the situation of government regulation. And it's probably appropriate that here at the Ford School there is a public policy and governmental angle or point of emphasis in this course. But government regulation is a completely crucial and often defective, often dysfunctional part of the process through which we provide for safe operations of dangerous industries. And a lot of the same organizational dysfunctions that we can identify in private corporations also occur in the context of government regulation. So regulators make the normal kind of routine organizational mistakes like inadequate training, inappropriate priorities, misuse of inspection resources, decision making within the organization that we might say objectively is a bad match to what the primary purpose of the agency is. But beyond these routine internal failures, we also have come to recognize that regulators are themselves subject to pressure from elected officials, from other government agencies, from presidents and senators and representatives and their staff. Regulators are subject to direct pressure from industry. And so there is always the possibility of regulatory capture in which industry can influence or control the contents of regulation, inspection, and enforcement. So what is normal accident theory? This is Perot's main theoretical idea. It's the main thing that you'll get out of these many, many examples that you have been reading out of the book. And I find the book completely fascinating. If I were in your place, I would read it cover to cover, but I've only asked you to read 4 or 5 chapters. This is his main theoretical idea. It is that modern society consists of risky, complex enterprises which involve complex processes. If you think about a chemical plant, for example, you have flows of materials at high pressure, high temperature, being controlled by pumps and valves and complicated plumbing. And a chemical plant, you might say, is just a paradigm of a system which can fail in unpredictable ways. There is the idea which Perot emphasizes, but it's an idea which is very familiar to engineering specialists, the idea that technologies differ according to whether they involve linear interactions, kind of one action occurs and then the next action occurs and then the final action occurs, or complex interactions where many processes are intersecting with each other simultaneously throughout the process. And Perot says that normal accidents often result from these complex interactions which were unanticipated. There is the issue of what he refers to as loose and tight coupling. So he talks about universities as being loosely coupled. So if there's a failure in the president's office to, get the documents for the promotion cases to the regents on time, that's a failure, but no lives are lost, and it's possible to simply defer consideration to the next regent meeting. So that is a loose connection, a loose coupling. A tight coupling is one in which processes are so intimately interconnected that if there's a failure to provide a particular input, then the next process is badly affected or maybe catastrophically affected. He also makes the point that normal accidents occur in systems in which it's possible or even likely that there would be multiple simultaneous failures. And if you've read anything about Fukushima, you'll know that there were the original events, the earthquake and then the tsunami, but there were also many other events which were somewhat unrelated, but which happened at the same time and created an environment where it was almost literally impossible for the operators to recover. So a normal accident is an accident in one of these tightly coupled, complex enterprises in which multiple conjunctions of unrelated happenings occur. And furthermore, he makes the point that these processes are often happening so rapidly that it's almost impossible for the operators to comprehend immediately what's going on. You probably noticed, I hope you noticed, in his account of 3 Mile Island, he goes through a dozen different events which have occurred, and then he says something like, this is minute 1.5 of the crisis. So all of that stuff had happened in the first, minute or so. He arrives at a gloomy assumption. It is that normal accidents are simply unavoidable. Now, this is a really gloomy conclusion, and one thought I would like to put in front of you is that in some ways it may be that Perot is overstating the impossibility of handling complexity, handling tight coupling. He's putting a particularly strong case, but I think part of your critical reading, both as you read the book, but also as we move through the semester, is to see to what extent do these gloomy conclusions really hold up 25 years later. And note that he first published the book, I think 1989 maybe, just a few years after 3 Mile Island. This point about incomprehensibility, that the failures which proliferate at Bhopal or at 3 Mile Island or at Fukushima, the pace at which and the multiple channels through which failures are occurring make it close to impossible for the operators to comprehend what is going on, let alone to take appropriate action to calm the situation, to end the process of accident proliferation. I introduced this diagram of what is, by contemporary standards, a relatively simple diagram of the power plant at 3 Mile Island. And you can pick out on this diagram the places where the 3 Mile Island disaster occurred, and it is a good example of a complex interaction leading to multiple failures. Perot says a couple of surprising things about the nuclear power industry, which we are now in a position to provide a better analysis, a better assessment of. He asks, for example, the question, why have we not had more 3 Mile Islands? He asked that question in 1984, 1989, when he first published the book, on the basis of about 20 years or 25 years of experience of nuclear power. And what he basically says is we haven't had 25 years of experience of nuclear power. We've had 6 months of experience with multiple different designs of power plants. And so we're nowhere near close enough to being able to evaluate and say we've got a long safety record for evaluating the risk of power plants. Power plants and design of power plants continues to change, and therefore the possibility of new accident scenarios is continually introduced. One interesting example, I think he makes use of this example, but in any case it's an interesting one, is the idea that it's the fact of corrosion. And evidently corrosion occurs much more rapidly in plumbing under conditions of high temperature, high pressure. And so a plumbing system in a nuclear power plant that was designed to last, let's say 25 years, may be hopelessly corroded after 4 years. And this was not planned for, it was not taken into account. And it means that there are new failure hazards in power plants which were not expected, not intended, and now need to be ameliorated. Perot also describes some more routine kinds of failures in the field of nuclear power.
Just a sec. Okay.
Plants. Perot offers more routine failures in nuclear power plants, which are also very chilling. But he talks about construction failures, for example, pouring of cement and leaving huge gaps. So just poor practices of putting down the cement, leading to containment vessels which are not structurally sound. Now, this would be a bad thing if you were building a highway. It is a catastrophic failure if you're building a nuclear power plant. But likewise, there are institutional and organizational, more or less routine dysfunctions, which have very important catastrophe or catastrophic results, or can have, in the area of riskier technologies like nuclear power. And one of those is the rush which the United States government imposed on settling on 1 or 2 reactor designs. They were very concerned in the 1950s to settle on designs so that it would be possible to validate the claim that atomic energy was a kind of an engine of peace. Well, one result is that the US and Europe settled on 1 or 2 designs of reactors, pressurized light water reactors, or the variety which Perot describes. And they were not necessarily the safest. In fact, they're more Rube Goldberg-y, with complicated additional safety measures needed because of inherent characteristics of the design. And a process which was a little bit more rational in terms of designing for safety first and rapid implementation second, in the long term would have been a better result. Defense in depth, one of the things that people want to say about the nuclear industry is the fact that nuclear plants have 2 or 3 or 4 levels of safety against foreseeable hazards. And Perot makes the point that, yes, we have actually prevented certain kinds of really serious accidents by having defense in depth, having, for example, very strong containment vessels. But we also have to recognize that even defense in depth is designed around what the designers refer to as design case events. And occurrences outside that envelope of what is a foreseeable or reasonably likely accident simply that's not taken into account. And that was true at Fukushima. So the design that was introduced for Fukushima to protect against ocean surge was prepared for, I believe, a 30-foot surge, which was higher than any surge that had been observed in the previous, let's say, 4 decades. A 40-foot ocean surge was physically possible, but it was not planned for. It was not part of the design case, and yet that's precisely what happened at Fukushima, leading to catastrophic results for the power plant. So let me close this. I've gone on longer than I normally would want to. Just a kind of interim assessment of Perot. I would continue to say he is just a marvelously astute observer of high-risk enterprises. I find all the cases that he goes through really interesting. And he has certainly identified a number of features of modern technology systems that contribute to the likelihood of accidents. He also makes it clear that there are deep interactions between the organizations that manage these complex systems and the behavior of the managers and operators and decision makers within those organizations, which can make accidents either more likely or less likely. The case studies offer lots and lots of evidence that is relevant to assessing that. So I would like to say that Perot's Normal Accidents book it's a pioneering book. It's kind of like one of the earliest contributions to what we might call safety science or safety sociology. It's certainly not the last word, and you're going to read some other really interesting people. I particularly like the work of Andrew Hopkins, who writes about the very undramatic industry of chemical plants and gas and petroleum processing plants. And his approach is really somewhat different, and we'll see some interesting differences between them. And there certainly are important aspects that Perot has not touched on. And I would also say that it's a good idea for you to be alert to the possibility that he is overestimating his pessimism about the logic of normal accidents as being simply inevitable, unavoidable, simply a natural and inevitable part of our technological future.